All right, thank you. As is common to many of these presentations, this is a huge collaborative work. I've listed some of the collaborators here on the first slide. Of course, Triton need not have any introduction to this crowd, so I can sit back and present some pretty pictures. On the left here is a NERCam early release observation showing Triton gleaming like a jewel next to the inner satellites of Neptune, and you can even see some of the faint rings showing up in this composite image. Now, Triton and Pluto have often been spoken of in the same breath. Insights from one have really motivated and served as a springboard for our understanding of the other. Jason gave a very good overview earlier today about the main similarities and differences. Overall, insights gained over many decades of observations, both from the ground and, of course, from flybys. And Triton and Pluto have both enjoyed high spatial resolution imaging that has really driven our detailed understanding of their surfaces and atmospheres. Triton has a very interesting orbit around Neptune. This high obliquity, high inclination orbit endows it with very strong seasonal variations in the subsolar latitude. On the upper right here, this is an image from Brian Holler's 2016 paper showing the seasonal variations in the subsolar latitude. This beating pattern is a sort of conspiracy between the precession period of roughly 680 years and Neptune's orbit. The period of the most high quality space-based and ground-based observations has corresponded to a particularly intense southern summer. Here in the bottom panel, this blue shaded region corresponds to the range of dates across which there was very consistent monitoring with the SPECS instrument on RTF published by Brian in his paper. So this is sort of our pre-JWST knowledge of Triton. It's a very complex surface, rich in hypervolatiles such as methane, N2, and carbon monoxide. But what really is the star of the show here that sets it apart from other dwarf planets is the abundance of CO2. And there's a whole slew of these absorption features that you can see clearly here in this composite of average of many IRTF spectra. So now enter JWST. So Triton, being sort of a big honcho in the KBO and TNO world, was included as an important target in the Cycle 1 Guaranteed Time Observations Program. And there were two observations targeting opposite hemispheres. The first one targeted the sub-Neptune hemisphere. This mosaic was created by Brian, overlaying the imaging from Voyager 2 onto the sphere. This red diamond shows the sub-observer position. The yellow line is the equator. And very faintly at the top, you see this green dashed line. And this gives the northernmost extent of sort of the extant published IRTF spectra. So we, in the years that have transpired since 2016, we've gained, about 6 degrees north in the sub-observer latitude, but in the sky projected plane disk, this is a very small wedge. So we're more or less seeing the same view as we have in the 2010s and early 2020s. All right, so let's jump into the results, shall we? So here is one of the two spectra from the GTO program. This is the anti-Neptune hemispheric view of Triton's surface. And you can see here right away that this entire spectrum is just replete with all of these wonderful absorption features from which we can really delve into the details of the composition and the physical nature of the different components on the surface. Up to 2.5, we had known already from previous slides. We saw the IRTF grand average. And the data that we get from JWST refines the spectral resolution and the fidelity of our view of the surface at those wavelength range. But what's really, really useful about this data is that we now have this full range beyond 2.5 all the way up to 5.2, where we have some of the strongest absorption bands of the key volatile species that are present on the surface of Triton. Particularly between 3 and 3.5, we have this primary band of methane ice. In it, we have distinct organic features, specifically ethane and evidence for C2H2, acetylene. We also have some interesting features due to isotopologues of the aforementioned species. We have 13 CO2 at about 4.37 microns, and we have 13CO a little bit farther down. So let's look at this spectrum in a little bit more detail. Here I've actually overlaid both the anti-Neptune and sub-Neptune spectra. They are to first order very similar. We'll get into the differences in a later slide. So the main scaffolding underpinning this whole spectrum is a combination of broad water ice features overlaid with a whole forest of these methane features. And this really establishes the core of the spectral diversity of this data set upon which some of the more minor features are overlaid. So here you can appreciate at the long wavelengths, we do have detections of the singly deuterated CH3D isotopolog. We talked about this earlier in the context of Eris and Makemake, but indeed, again, we see this isotopolog in Triton spectrum from which we will be able to derive a D to H ratio. So the star of the show, once again, is CO2. In addition to this fully saturated nu3 primary band at 4.25 microns, we have at least 20 overtone and combination bands detected in the JWST spectrum. We have the triplet around 2 microns that was previously seen in RTF data, but also a really, really interesting region between 2.6 and 2.8 with 2 of the strongest overtone bands, very clearly resolved. The detailed structure and even some of the subbands are also very clearly seen. As I mentioned before, we have 13CO2 at about 4.4 microns. And in addition to the CO2, we have CO2 isotopologs, 12CO and 13CO. Unfortunately, the main N2 feature is in the gap between the detectors. These are high spectral resolution observations. But there's some of the N2s mixed into that saturated 12CO2 feature in the bottom panel. Okay, so Triton also has an atmosphere. This is, of course, not new. This was imaged during the Voyager flyby and also studied in subsequent occultations and radio measurements. So this plot here provided by Emmanuel Lelouch is a continuum fit above which we can see the clear fluorescence peaks due to CO in the atmosphere. So he has provided us some preliminary modeling to try and understand what is the mixing ratio of CO and whether we see any of the isotopologs, and indeed we do. The red curve in the left plot is the composite model. The residuals are very flat, indicating that even this relatively semi-empirical model it's not an optimization, sort of a brute force matching of the peaks, nevertheless give us a really good handle of what is going on with the CO and in Triton's atmosphere. On the right, we have a breakdown of the different components. In blue is the 12CO fluorescence band, the main band. We have the detection of the hot bands of CO, the 2-to-1 transition in red, as well as a combination of 13CO and a small admixture of C18O. So we have both the heavy carbon and the heavy oxygen isotopologs of the gaseous CO in Triton's atmosphere. So work has continued to be done to refine this model with a more rigorous physically motivated approach, but this gives us a general picture of the atmosphere. For those interested, the mixing ratio of CO in this model is 1,000 part per million, in agreement with Emmanuel's 2010 paper. As I mentioned before, there is evidence from ground-based observations that there is significant longitudinal variations in the abundances of ices across Triton's surface, primarily the hypervolatile species N2CO and CH4. Here I've aligned the sub-Neptune and anti-Neptune spectra, just kind of small windows in the wavelength range where you can really see the variation in the depth of those features between the two hemispheres. So the deeper the feature, the more abundant it is, or the stronger the signature. And we see systematically that the anti-Neptune hemisphere is depleted in the hypervolatiles, particularly N2 and CO, relative to the sub-Neptune hemisphere. Meanwhile, both H2O and CO2 do not show appreciable longitudinal variation. This is all consistent with work by Will and Brian over the past decade and a half, combining all this photometric modeling, spectroscopic modeling of Triton with IRTF. So this is a figure from Brian's paper once again, showing the insights gained from this ground-based monitoring, and they've been able to pinpoint the longitudes of maximum signal for all of the important volatile ices, we see that N2 and CO sort of coincide with the leading sub-Neptunian quadrant, whereas CH4's peak signal is about 90 degrees offset, still in the sub-Neptune hemisphere, but on the trailing side. Meanwhile, there are very little constraints on where the maximum CO2 and H2O signals are because they do not show appreciable longitudinal variations. So another big feature of Triton is that we know the abundance and strength of the signals for the hypervolatiles has shown secular variations over the past decade and a half, actually more than 2 decades now. So this is a follow-up work in combining more recent observations with IRTF, and this is graciously provided by Brian and will be summarized in a paper that he is leading on the IRTF data since his 2016 publication. So what I've done is I've done a simultaneous sinusoidal fit to the longitudinal modulation alongside a polynomial fit to the secular variations, temporal variations. We find very strong signals of increasing band areas for both CH4, N2, and now CO. And in addition, we find that instead of a linear trend, there's evidence, very strong evidence from a statistical standpoint, that this increase in the band area is accelerating as the sub-observer latitude is increasing into the lower latitudes in the southern hemisphere. So this is ongoing work, and this will be refined further on. Okay, so let's step back and look at the bigger picture. The Triton joins Makemake, Eris, and Pluto on one side of this so-called cosmic shoreline, to use a term that people in the exoplanet community like to throw around. But nonetheless, we see a clear transition among these largest dwarf planets where they show very strong signatures of the hypervolatiles. And this is an old story that has been sort of rehashed in recent years with new vapor pressures. And this particular iteration is a figure provided by Sylvia Protopapa, prepared by Perry and Johnson, showing the essentially the stability lines of various volatile ices. And we find that N2CO and CH4 really delineate this transition between these large dwarf planets that show the hypervolatiles and smaller objects such as Charon, which are dominated by CO2, water, and more refractory species. So Noemi showed this plot earlier in the morning. This is a compilation of the JWST spectra for these 4 largest dwarf planets. And we see a continuum in the relative strength of methane ice, starting from Triton, which is the most methane poor, all the way down to Makemake, which is much more dominant in methane. And we see a range, this implies a range in abundance and perhaps also effective path length, as well as a range of the relative admixtures of other minor components. We know Triton has strong CO2, whereas Makemake and Eris do not show any CO2. So being a Pluto conference, you know, I need to compare Pluto and Triton, of course. Yes. Is this 2 minutes of the 15 or 2 minutes of the 10?
2 minutes, including questions.
Oh, okay. So very quickly, here are the JWST spectra of Triton and Pluto next to each other, where you can appreciate once again the very different strength of the methane ice absorptions, and also the much stronger CO2 on Triton. Zooming in on the atmospheric features is a really interesting endeavor. We see here in the CH4 fluorescence region, we have Pluto showing very clear signatures of the atmospheric methane, whereas we don't detect any fluorescence bands of CH4 on Triton. And this is not surprising because the mixing ratio of CH4 on Triton is expected to be more than 10 times lower than that on Pluto. Meanwhile, in the CO fluorescence region, both objects show very clear fluorescence bands. One key difference in Pluto is that the hot bands of CO are much more prominent, as well as the heavier isotope fluorescence bands. And modeling is still ongoing for both of these objects to try and tease out the exact details of their atmospheric properties. So with that, I'll take some questions. Thank you.
All right, we have time for one question.
Near its Q branch, atmospheric methane absorption. Have you looked for atmospheric methane absorption near its Q branch in the 2.4 micron region?
So we do not see any signature of in either emission or absorption in the Q branch at around 3.4 or shorter.
Thank you, Ian. Thank you again, please.